In this lecture, we will learn the Fourier series representation of the continuous time signal x of t. So our target today is the Fourier series representation of a continuous time signal x of t. And as you can see, a couple of equations are available here. In the first equation, if you concentrate on x of t, the left hand side is a time domain signal x of t. Here we are assuming that it's a periodic continuous time signal, a time domain signal. And on the left hand side is x of t. The right hand side of this equation is actually a summation. You have a summation of complex exponentials, right? So you have basically a summation of complex exponentials, and you can see this summation, the running index of the summation is k, and you can see a coefficient over here as well, a sub k, which is actually it will be some the coefficient which is known as the Fourier coefficients, and this equation basically is a Fourier series representation of x of t. You represent what if you will go deeply into each and every term of this equation. For the time being, you can see that actually x of t is represented as the sum of infinite terms, and these terms are actually the complex exponentials, right? And each complex exponential is scaled by a sub k. So basically it's a the equation has infinite terms, and these infinite terms, these are the terms which are actually added. You have k varies from minus infinity to plus infinity. So this is the these are the limits of k, and you can just substitute different values of k and expand this summation if you are interested in writing instead of a compact form. If you are comfortable with writing it, expanding it for different values of k, so we will see with the help of an example. So this is actually the Fourier series representation, which we will see in more details. It means now you can observe it, visualize it. You can visualize x of t as the sum of complex exponentials, and you should be well aware from our previous theory that this exponential can be written in the form of sinusoids, right? Now what this ak, these are, as we say, these are the Fourier coefficients which act as a scaling factor here for the amplitude of this exponential. Ak can be computed from this equation. So these are ak's for different values of k, for 1, -1, 2, -2, 3, -3, because k varies from minus infinity to plus infinity. So you can compute ak by 1 over t, because we are talking about the periodic signal, so it will have a period t. So it would be periodic with period t, and you have to compute this integral, the product which has the product x of t multiplied by e raised to the power minus j k omega naught t. Well, we will see this shortly in details, but before going into the calculations of these AKs, let's try to concentrate on this equation and try to see some signals x of t as the summation of complex exponentials, and we would like to visualize those signals so that we can see the waveforms of x of t, which can be represented as a summation of complex exponentials. So I'll go to the fresh slide, the new slide, and let me before starting the Fourier series in more details, let me solve some mathematics. Let me solve some mathematics. So let me recall a few things. You are familiar with the from your elementary classes, you are familiar with the Euler identity e raised to the power j theta, and you can write it, if you recall, it's just cos of theta plus j sine of theta. So if you now from here you can have multiple identities. If you substitute, substitute minus theta, if you substitute theta is equal to, instead of theta, if you substitute minus theta, right? If theta is equal, if theta is negative, or let me say if theta is negative, let me say if theta is, if theta is, put theta negative, right? Put theta or let me write it clearly that if your theta is negative, then this expression would be e raised to power minus j theta, and cos of, you will have cos of minus theta plus j sine of minus theta, right? And you can rewrite it, e raised to power minus j theta, which is cos of minus theta is same as cos of theta, right? So you can compute it, same as cos of theta, and sine of minus theta is the negative of minus sine theta. So if you write minus, it would be minus j sine of theta, right? Sine of minus theta is actually equal to minus sine theta. Sine of, let me write it here, sine of, you should know that sine, or let me write it with the same equation, that sine of minus theta is equal to minus sine of theta. This is same as minus sine of theta. Now you have two expressions, this one and this one, e raised to power j theta and e raised to power minus j theta. Let me call it 1 and call it 2. So if we add 1 and 2, what do you get? If we add 1 and 2, you would actually have e raised to the power j theta plus e raised to the power minus j theta equal to 2 times cos of theta, 2 times cos of theta, right? And you can rewrite it, instead of writing this 2 there, let me rewrite this 2 here. You can rewrite it, here, right? So you have cos of theta is equal to e raised to power j theta plus e raised to power minus j theta over 2. And similarly, if you subtract 2 from 1, so if you subtract 2 from 1, let me subtract 2 from 1. So if you subtract 2 from 1, let me write it here, 1 minus 2. What would you get? You would get e raised to the power j theta minus e raised to the power minus j theta, which would be equal to 2j times sine of theta. You would get this one. And if you divide both sides by 2j, you would get the expression for sine of theta, and the expression for sine of theta would be a 2 here. So this is basically your sine of theta, e raised to power j theta minus e raised to power minus j theta over 2. So you get these identities. From Euler identity you can get these expression. Now you can see that you write the exponentials, right? A complex exponential in terms of sine theta and cos theta as well, right? Or alternatively you can say that sine theta and cos theta can be written as the sum of exponentials, the sum of complex exponentials. Now with these two with this concept, we would see it would be easier for us to visualize the above equations, the equation for the Fourier series more deeply. We will see it shortly, right? Let me give you another let's recall that if you have an x of t, if you have x of t, which is e raised to power j omega naught t, right? So this is, now you are familiar that if I say e raised to power j omega naught t, you can write it as cos and sine, cos of omega naught t plus j sine of omega naught t, right? And this we have proved already. It's quite easy to prove that this is actually periodic. This is actually periodic with a period t. So you can say that your omega naught t plus, if it is periodic, keep in mind, if it is periodic, x of t plus t should be equal to x of t, right? If it is periodic, these two should be equal. These two should be equal, right? So let's try to see whether it is periodic or not. So if you want to find, put t equal to 2 pi. Suppose I say t equal to 2 pi. So there should be some positive t for which this signal is periodic, if it is periodic. So let's see whether it is periodic or not. T plus 2 pi, and you can rewrite it. You can rewrite it as x of, you can rewrite it as e raised to the power j omega naught t, e raised to power j j 2 pi, right? E raised to power j 2 pi. So this is what you can this is actually the signal x of t plus t. So this is the signal x of t plus 2 pi, capital T. So just substituting this one, and you can you are familiar with this one. This is actually equal to e of j omega naught t, and you can find it out, cos of 2 pi plus j sine of 2 pi. Sine of 2 pi is 0, right? This is 0 and this is 1. So you are left with e raised to the power j omega naught t. So it means that the signal e raised to the power j omega naught t is periodic with a period t equal to 2 pi, right? And it's not only t equal to 2 pi, but multiple of 2 pi. The same signal is periodic with the period multiple of 2 pi. So basically, the complex exponential e raised to the power j omega t, if x of t is this one, it's basically a periodic signal. We have seen this one earlier. Similarly, we have seen and we can very easily prove that if the signal is cos of omega naught t, this is also a periodic signal with a period capital T, a positive T, which is 2 pi or multiple of 2 pi, you can say. So this is also a periodic with period 2 pi. So these are the examples of periodic signal which we will encounter definitely in our discussion. You have a set of, you can also define a set of signals phi k of t, which is e raised to power j k omega naught t. Now you can say that, okay, my k may be 0, maybe plus minus 1, plus minus 2, and so on. You have multiple values of k, and you can always prove that these functions phi k of t, all of these functions phi k of t, all of these signals, all of these waveforms are actually periodic. All of these waveforms are actually periodic. You can always prove this, that all of these signals are periodic. So keep this in mind, because these functions are used in the Fourier series, and these complex exponentials, you can say that these complex exponentials actually can be viewed, they can be viewed as sinusoids, if you the sine and cosine waveforms which are real signals. So, now suppose we have a signal. Let me show you a real signal. Let me show you a real signal. Let's try to solve an example of a real signal, uh, which can be written as a summation, of, let's solve an example of a real signal x of t, which can be written as a summation of for k minus 3 to plus 3 a sub k e raised to power j k omega naught t. Suppose we have this signal, and let's try to give some values here as well. Instead of k omega naught t, let me give some value. Suppose we have k k 2 pi t, k 2 pi t. So we have known frequencies, right? Fundamentals. Now for k, keep in mind, and with this expression, suppose we are also given that a naught is equal to 1, and suppose a1 and a of minus 1, they are equal, and both are equal to 1 by 4, and suppose a2 and a of minus 2 are also equal, and they are given 1 by 2. Similarly, a sub 3, a sub minus 3 are equal, and it's given that these are equal to minus 1 over 3. Suppose these are given. Now let me try to expand this signal so that you can see the signal clearly, right? So with these coefficient, we are trying to visualize these signals, right? So we are given that a naught is 1, so we can write our x of t, because it's a summation. So you can say, okay, for k minus 3 to plus 3. So let me try one by one. If k is minus 3, I would have a of minus 3 e raised to the power j k. K is minus 3, and then we have 2 pi, then we have t, right? Minus 3, which is actually 6 pi. Then I can write another one for a minus 2, and the exponent will be e raised to the power minus j 2 times 2 pi t. Then I can have another term which is a of minus 1 e raised to the power minus j, k is 1, so 2 pi and t. And then I can have another term which is a naught, and e raised to the power 0 would be 1, so I'll just write a naught. Then I have another term a of 1. Let me arrange it in such a way, because all these are added, so I arrange it in such a way that additive term I'll write below a minus 1. So I have another term a1 when k is equal to 1, and that will be e raised to the power j 2 pi t. Then I'll have another term which is a of with k2, so that would be a2 e raised to the power j 2 times 2 k is 2 pi and t. And I'll have another term with when k is 3, it is equal to e raised to the power j 3 2 pi and t. Now this is how I expanded that summation x of t, and with this expansion you can see that my x of t, let me bring it below a little bit. So x of t, let me rewrite my x of t, and I would write it over here. X of t. Now you can see, just substitute these values. We just put the values of k only. Now the values of a sub minus 3, a sub minus 2, these values are also given. So if you observe these values, a minus, these values are also given. So we can just substitute these values. Now in this equation, I would like to substitute these values as well. So if you put these values, let me put it here, a of minus 3, right, and a of 3. I'll put the values of a of minus 3 and a of 3, and that is given 1 over 3. So I have 1 over 3 here and 1 over 3 here. Similarly, you can see that a of minus 2 and a of 2 are also given, and those are 1 over 2. So instead of writing a of minus 2 here, instead of writing another line, I'll just replace these values, 1 over 2. So let me write 1 over 2 here and 1 over 2 here. And a of 1 and minus 1 are also given. So I would replace these by a of a 1 over 4 and 1 over 4 here, and a naught, instead of a naught, this a naught, let me write its value, which is 1, right? So we can write the value of a naught, and let me erase a naught here, and I would like to write its value, which is 1, right? Now if we rearrange these terms, we can just take 1 over 3 common from these two terms, 1 over 3 common from these two terms. So let's try to take 1 over 3 common, and we rewrite our equation. So I'll write here 1 over 3, and inside the brackets I have e raised to the power j 6 pi t plus e raised to power minus j 6 pi t, right? So this is the term from these two. Similarly, I can combine the other two by taking 1 over 2 common from the next two terms, which are this one and this one. So these two, take 1 over 2 common and write these jointly. So you will have e raised to the power j 4 pi t plus e raised to the power minus j 4 pi t, and this is the third term here. We have another one from these two, 1 over 4 we can take common. So let's try to take 1 over 4 common, which I can write over here. 1 over 4 is common, and I have e raised to the power j 2 pi t plus e raised to the power minus j 2 pi t, right? And I have a 1 over here. Now if we use our the knowledge of Euler identity, we can, let me rewrite it in the next line. I'll write 1 first, right? 1, then I'll write this term. I'll write 1 over 2 times, you can see, let's try these terms one by one. So try these. 1 is in the beginning. Now try to observe this term. This e raised to power 6 pi t plus e raised to power minus j 6 pi t, but over 2 is missing. So let's try to divide and multiply this term by 2, right? So if I try to divide this one by 2, and I write 2 here, right? So I can rewrite this term as 2 over 3 cos of 6 pi t, cos of 6 pi t, right? Now let me see the next term, and if you observe this one, it's quite perfect. You have e raised to power j 4 pi t plus e raised to power minus j 4 pi t over 2. So I can write here that my next term is actually equal to cos of 4 pi t. And if you observe the last term, which is 1 by 4, this one, So just write it this way, put 2 here and 2 here, it's still 1/4. So you can see that this is actually equal to 1/2. It is 1/2 cos of 2 pi t. Now x of t, which were now you can observe your x of t. Observe this x of t. This is your x of t, and your x of t is actually the summation of 4 signals. One is constant, the second one is a sinusoid, cosine wave with certain frequency, another one and another one. 3 sinusoids and a constant. So it's actually an addition of these 4 signals. So let's if we try to try to see these expressions now, let me bring it a little bit below. So these summation, let me try to draw these signals. So if I draw my constant, I would draw that my constant is a time signal 0, and this signal remains constant 1. This is the first signal, which I may call x naught of t. Suppose this is my first signal, x naught of t. My second signal, if you observe closely the second term, this one, or instead of taking this one, let's try to take this one first, whose frequency is lower than that, cos of 2 pi t. Let's take this term. So this, let's call it x. Suppose this is my x1 of t. So my x1 of t actually has a frequency of 1 Hertz, because if you compare it with cos of the standard form, cos of 2 pi ft, so your frequency in Hertz is just 1 Hertz for cos 2 pi t. So your frequency is actually 1 Hertz. So you have a sinusoid, you have basically a sinusoid, a cosine wave which has a 1 Hertz frequency. So it's a sinusoid having 1 Hertz frequency, something like this it would go, right? This is my second signal, which is x1 of t. Suppose this is my x1 of t. Now I have the third signal, which has a bit higher frequency, cos of 4 pi t, and here the frequency, if you observe, the frequency is 2 Hertz for cos of 4 pi t. So I can write the fourth the x. Suppose this is let me say that this is my this is x2 of t. Suppose this is my x2 of t, cos of 4 pi t. So we can draw another signal which has a frequency of 2 Hertz. So it would it has a frequency of 2 Hertz. Now x1 of t, keep in mind x1 of t, for x1 of t, let me recall this one. For x1 of t, this amplitude is 1/2, so the peak here is half, so it oscillates between half and minus half, right? x1 of t. But if you observe x2 of t, here it is 1, so it oscillates between 1 at a higher frequency. Let me it's not very perfect, the drawing is not very good. So it's at a higher frequency than the other one, 2 Hertz frequency, but it will oscillate between +1 and -1, right? It has 2 Hertz frequency. It has 1 Hertz frequency, this one has 2 Hertz frequency. Not very perfect here in this diagram, but keep in mind that the frequency for x2 of t is 2 Hertz. Now you can write x3 of t, which is cos of 6 pi t. If you observe, suppose this is my x3 of t, the third one. This is x3 of t. 2/3 cos of 6 pi t. So it would oscillate between ±2/3, and the frequency basically for x3, if I want to plot x3 of t, so let me plot x3 of t, and it has a much higher frequency, right? Much higher frequency, as is actually the frequency is 3 hertz in that case. 3 hertz, it's 2 hertz, 3 hertz for x3 of t. So basically your x of t is the summation. It is the summation of the constant and 3 sinusoids. It's basically a summation of these. You can see that complex exponential. Earlier we saw that our x of t is the summation of complex exponentials, right? It was in this form, from -3 to +3. We had a, k, and e raised to the power minus j 2 pi t, k 2 pi t, k 2 pi t. So it was in the form of complex exponentials, and now we can see the same x of t as a summation of sinusoids, a cos term, right, with some constant here, then another cos term with some constant here, and let me write that constant. Let me give it, suppose this is a constant c1, this is c2, and another term with a constant here. We are viewing that x of t as a summation of these sinusoids. So you can see that these complex exponentials basically are sinusoids. For we have a real x of t and all are cosine waves, right? Or are cosine waves. When we have we can do the same for sinusoid as for sine signal, which is just a 2 pi by 2 shifted version of the cos wave. So well, this is in this example what we learned that the signal, the complex exponential, can be viewed as the sum of complex exponentials. They can be viewed as actually these are sum of sinusoids, right? These are sum of sinusoids. So this was the basic theme. So let's try to solve a few example in the next slide, and we would try to determine the values of AKs. We would like to determine the values of AKs. Here AKs were given. In the next slide we would like to determine the values of AK using the Fourier series Fourier series representation. We would try to determine those AKs using integral and comparison as well.